Hello everybody. Today I'll be talking to you about effect of adding weights and removing weights, it's loading and discharging on a ship. This is something that you all are aware of. It just a recap that if you have a area, the geometric center of that area is basically the centroid. And then we talk about center of gravity. Center of gravity is the point at which the mass of the body is assumed to be concentrated, and it is the force, gravitational force, which is acting downwards from the center of gravity, and we consider that to be as weight as mass into g, that is your acceleration due to gravity. And center of gravity is the point on which you can balance the uh, any object, a geometrical object which is homogeneous. It can be uh, balanced at its center of gravity. Now, like this was something which we all tried it on our school days without realizing what was center of gravity. We used to take a scale and just try to balance it on our finger, and we used to be very happy about it without really realizing that it's something to do with center of gravity. Now, instead of this scale, let us just talk about a homogeneous plank. Now, this would balance somewhere right in the middle. That is what I talked to you about, balancing your scale there. So, for a homogeneous body, homogeneous plank, center of gravity is at the geometrical center. So that will be at half length, breadth, and height. Now, moment of forces, again, is the turning effect of the force about certain point. And we calculated with force into distance. Now, this moment depends upon, as the formula suggests, on the force and distance. Now, force, when we are talking here, we will be talking about weight. So I'll not talk about mass into acceleration due to acceleration, but we'll be talking about mass into acceleration due to gravity, that's weight. And the distance, the force, and in this case we are talking about weight, is from the point about which we are trying to calculate our moments, the distance. This force is the weight as far as we are concerned here, and the distance around which we are measuring the moments. And moment is weight into the distance from the point around which we are talking about the moments. Let us just consider the weight of this plank as W. The moment what it is going to make is W into D. Now the weight, when we are talking about the weights are at the center of the gravity, because the weights are, as we just talked about it, that uh, they are concentrated at the center of the gravity. So for us, the distance would be from the center of the gravity of the weight what we are talking about. So if it is a homogeneous plank, as we just said, it will lie at the center of the homogeneous plank, somewhere here, halfway through the scale. I've used the scale purposely so that the things are clear to you. So if this is a homogeneous body, the center of gravity will lie right in the center. That is when I'm showing you the scale of 0 to 12 inches or 0 to 30 centimeters. It will be right in the center, 6 inches or 15 centimeters. And the weight is downward from here. So the moments are going to be created from the point what we are talking about. But let us consider that this edge of the scale, the moments created by this weight would be W into the distance. Here the distance is 6. I mean, I'm not going to talk about it. This is going to be inches or centimeters. So the moments created by this is W by 6. Now if we just balanced it, so the the uh, the plank is going to be balanced, so it will be creating equal moments on either side. Now you have half the weight on one side and half the weight on the other side. Now the center of gravity would be halfway through from here to here. That is going to be 2 plus 1. You take it as inches, or when we talk about in centimeters also. So it will be the weight is concentrated at G, the force is going to be at G, and its distance from the point around which we are talking about the moments, the distance. And here the distance we are talking about is 3 in terms of inches. So the moments are going to be W into half the weight into 3. And the other side is also going to create the same. The total moment what has been created by this weight still comes to the same what we have calculated here. So the moments are created by the weight and the distance from the center of the gravity. Now let's consider this plank. There is center of gravity lying right in the center, halfway through the length and height. Now let's talk about this piece. Now I have divided this into small compartments, which are of 2 centimeters each. What you can see here now. Now this part of the homogeneous plank would have certain weight, which I have taken as a small w here, and the weight will be acting downwards from center of gravity of this uh, block. This is going to be some distance away from the fulcrum, from the point around which we are talking about finding out the moments. And it will create a moment. If I remove it, it is going to create certain moment, which is going to be W into D, whatever the weight was, and the distance from the center of gravity. Now this, as soon as I have removed this, it is going to tilt. It's creating a tilting moment anti-clockwise. Now to balance this again, the D should shift to new half length of this, which is now it is 10 centimeters, should be somewhere here, then it will balance. So here we see that once I have removed this weight, my center of gravity is moved to new center, new half length of whatever the scale is, or halfway through, and it's moved by about 1 centimeter here, what we can see. So what we noticed here, that as we are discharging the weight or removing the weight, the center of gravity is moving away from the weight discharged. It is moving in the opposite direction of the weight discharged. Similarly, if I just added this some other weight here, now my scale has gone to 14 centimeters. Balance it again, because this weight will create certain amount of clockwise tilting moments, and compensate for this, to have it balanced, the G should shift to new half length. It should be 7. And now it will be balanced. So what we have seen here, that when we have added the weight, the center of gravity has moved towards the weight loaded. So this is something what we should always remember, that the weight are added, the center of gravity goes towards that side, and if there's discharged, they go away from there. And this example, we have a scale of 12 centimeters here. This side is going to create certain moments from the center of gravity, because the weight is concentrated at the center of gravity, and that would be W into G. D. And the other side also being balanced would create the same moment, W into D, which is the weight on the other side, small w here. Now this particular scale, now just trying to explain it the other way around. Just made this part of the scale as 20 centimeters long, and let's say that it's 1 kg. Now, being a homogeneous part, center of gravity would be right in the center, which is 10 centimeters away from either side. It's right in the center, 10 centimeters. This full scale is of 120 centimeters now. And the weight, I've taken one weight as 1 kg. So if you look at it, there are 6 things. The total weight would be 6 kgs. And as we just talked earlier, that the center of gravity would be half length. So we'll have the center of gravity at 60 here. Now look at this weight here. This is 1 kg, and its distance from the center of gravity, it's the center of gravity of this is 50 centimeters, because 20 and half of it, 50 centimeters. Being 1 kg weight, it will produce a momentum of 1 into 50, that's 50 kg centimeters. Let me remove this. Once I remove this, this has given me a tilting moment of 50 kg. Now we just saw that the shift of gravity when you're discharging weight is going away from the center of gravity of the discharged weight. So as you can see it here, that now the scale has become 100 centimeter, it will balance at 5. So the center of gravity would move away from the weight removed. It is a new length, and it moved by about 10 centimeters. Now the moments are the turning effect about the point, isn't it? So the new weight is now 5 kgs, and the center of gravity would be halfway through. Now the weight is concentrated here at 5. So the force is going to be from this point here. And this here is creating a moment of tilting equal to this. When it is being tilted, how is it being tilted? Because the moments are being created at G from G dash. And the moments are equal to whatever the weight is into the distance the G is shifted here. Now for the this blank to balance up, this moment here and this moment, what it is creating has to be compensated. They both should be equal. So what is this final weight and the distance what the G is going to move so that I can balance the weight is going to come up something like this. W into 2. And what is the distance what I've got to move would be the moments and anti-clockwise moment what was created divided by the new weight. And the distance what G has shifted here is 10 centimeters, what we just saw. So to find out what is the shift of G by removing a weight or adding a weight, you can calculate it by this, the weight, what is removed, its distance from center of gravity, and the final weights. I have added and subtracted, shown you added and subtracted, because it is going to be the reverse of what I'm showing you here in case of removing the weight. But the final weight would be whatever the weight is remaining, either added or subtracted. And this you can see how we have calculated here. formula was 50, 50, which is W into D divided by minus weight is 5, and you get an answer this. So to calculate what is the shift of G, the formula what we use is the weight, discharge or error, and its distance from center of gravity divided by final weight. Now let us see how it is applicable on the ship. Now here is the ship with a displacement, that's the weight of the ship is delta, what I have shown you here, and with the center of gravity right here. And we just saw that by discharging the weight, the G goes away, and by adding the weight, it moves towards the weight what is added. So let me just add a weight here. So what we said, just said, if the weight is added, then the G should be moving towards the center of gravity of the weight added, and the distance what it moves is calculated by whatever is the weight of the load in the distance between the center of gravities divided by the total weight. Here in this case we have added, so I have just added it up here, and here minus if you discharge the weight, and center of gravity moves towards the weight loaded. I'm loading it on top of G. As we said, it should be G should be moving up, and the distance would be according to this formula here. Similarly, weight loaded onto my starboard side, the G would move towards the center of gravity of the weight loaded, and the distance, how much this G is going to move, again this formula comes into play. Now, weight loaded here, this is the distance from center of gravity, so it will move towards the weight loaded. Now let's discharge, and whatever is what we have talked about it, it's going to be opposite to this. This is the distance. How much the G is going to shift will depend upon what the distance is and what the weights are, and it will move away from the center of gravity of the weight discharged. So it will move here. And if there are weights to be shifted on board, which are already there on board, no loading, no discharging, whatever is there, then the shift of G is in the direction in which the weights are shifting. If I'm going to shift the weight down, this G would move down. If I shift the weight up, it will move up. If I move it port starboard side, it will move port and starboard. So let me just move this weight in the direction of this arrow what I'm showing you here. So the G would also move parallelly to that in the direction the weight has moved. Now you see, this is one thing what people have a little doubt about it. So we talk about, let's talk about a pulley. We have all seen some blocks, and we lift some weights with this, lifting some weight with the block. Now I'm not going to be talking about the resultant forces or parallelogram of forces or etc. anything like that. Just uh, visualizing, trying to think about it. Where do you think the weight should be acting? Where should the whole weight, suppose you have a weight which is being pulled up and you're pulling it in this direction, where do you think it should be? As far as I think, logically speaking, it should, the whole weight should be concentrated here. So When you are lifting any weight with with the ship's gear, the center of the gravity of the weight automatically goes to the thing. And as we said, it is halfway through. When we talked about if it's a homogeneous weight, it is half length. So this length and this length, halfway through would be the block. So the center of gravity would come to the head of the lifting gear. When the weight is suspended, the center of gravity comes up right on to the point from where it is suspended. Now, just an example of how your ship center of gravity moves around. Consider this to be a ship and it is alongside. You have some weight on the ship X and it's got a center of gravity A. Now, and the center of gravity of the ship is here somewhere G here. This weight has to be lifted up. So, as soon as you lift this weight up, the center of gravity goes to the point on top. So now, as soon as the weight is just lifted up, doesn't make a difference. You lifted it 1 centimeter or 5 meters, the center of gravity will go right on top. Now, let us see how much the center of gravity is going to move. Again, whatever is the weight and the distance. Now, in this case, the distance, if the center of gravity of A was A and center of gravity of this was B, the distance would be B minus A. So if I said that this is 20 meters and the weight was at 10 meters, the distance between them would be 10 meters. So the CG of the weight would go higher by 10 meters. And as soon as the weight has been picked up, as I said, irrespective of the fact that it is just 1 centimeter or 10 centimeters, 1 meter, the G would move up because now it is a situation where the weight is being loaded on top of G because the G has come here, the whole weight is concentrated here, so G would move up. Now let us get it over the side, to the side of the key. What has happened? G2 is come here now from G. First the gravity was here, the center of gravity is here. This is the direction what the G is moved. So G would also, the ship's gravity, center of gravity would move parallel to this in the same direction towards the weight, and you'll have the gravity, center of gravity here. Now if I discharge this weight, as soon as I discharge this weight, what has happened? After discharging this weight, the center of gravity goes away from the weight. That is what we saw. Once we discharge, the center of gravity goes. So you'll have final G3. And the final of shift of G would have been from G to G3 and would be calculated with whatever the weight was and the center of gravity of A divided by what is the weight now. And as you can see, when we talked about it, we lifted the weight from here, we discharged it. The center of gravity of weight was here, whereas this gravity moved. Once it is discharged, it's moved away from the center of gravity of the weight concerned here. On the ship, when we measure everything, we measured in from keel. So all the moments are taken around the keel, and we talk in terms of kg. So kg is basically the center of gravity of uh, any mass what we are loading on the ship, discharging from the ship, off the ship, kg. We refer to it as kg, so we don't talk cg, we talk in terms of kg. So kg is basically nothing else but the distance of center of gravity of whatever mass we are talking about from the keel, as we measure everything, all the moments around the keel. Just an example here given to me that the ship has a displacement of so many tons and kg, 6 meters. Now a load which is there 40 tons, it's got a kg of 3 meters, it's already on board. So let us consider that we have a weight which is here, and this kg, that is from keel to the weight, is 3 meters. Now it is raised 1.5 meters vertically by the ship's crane, whose head is 17 meters. So we have a crane whose head is 17 meters, and we are going to lift this weight, and it has been lifted 1.5 meters. Now, as I said, as soon as the weight is taken by the crane, irrespective of the fact how many meters or how many centimeters it has been raised, the center of gravity of that mass goes right to the head of the crane. So these things about it is raised 1.5 meters, it is raised 6 centimeters, 10 centimeters, 1 meter. That's all a confusion. The thing what you got to remember that as soon as the weight is taken up by the crane, the center of gravity automatically goes to the head of the crane. So here, as soon as the thing is being lifted up, I'm not talking about 1.5 meters or whatever it is, the center of gravity would go to this point, that is 17 meters. He wants me to find out the new kg. Now here, the center of gravity is gone here, it is 17. The center of gravity of this body was already 3 meters. So what is the distance what the center of gravity has changed here? It's 14 meters, not 17. Now I'll not talk about head because it is already the mass already had a kg which is 3 meters above the keel, and the height of the crane is 17 meters above the keel. So the distance what the center of gravity is going to change from 3 to 17. That's 14 meters. So this is another important point what you should see, remember. And then we talk about the shift of G is weight into the displacement or weight of the ship. Now this weight was already there on the ship, so there is no change to the weight of the ship here, displacement of the ship. So the shift of G we calculated by weight into the distance divided by the displacement, which is 0.8, and the final G. Now in this case you can consider this part of it because now this weight is come above the center of gravity. As soon as you lift it up, the weight has gone here. So it is something like adding up weight. So the center of gravity would move up in the same direction where the weight is added. So the final kg would be, what is your initial kg plus this. Now let me just rephrase this question because in the book it is only up to this place. Let's rephrase this and ask what is the kg after completion of the operation. That means now completion of operation means that you have discharged this weight, right? So now the shift of G would be calculated with whatever is the weight into the distance, the D. What is the center of gravity of this? Because now when we are talking about completion, now the weights are not, we are not talking about weights here. Now the weight has already gone, landed ashore. So now what is the shift of G? Whatever is the weight into its center of gravity here divided by the new displacement, which is minus the original displacement. And that would be the shift of G. And here I am removing it. So the G has to go on the opposite side of the weight. So the weight was 3 meters, which was below 6. So it has been removed from here, somewhere below from here. So when we talked about the weights had to be discharged, the G moves away. So the weight should be moving up. If case the weight was here, then the kg would have to be subtracted rather than what I have added up here. Thank you very much. Continue.